behind my back right now. I'm just going to dive right in to R6. It's still, I'm going to see how the lecture goes at this point, because we were already behind even if I hadn't gotten sick, so the dates are just kind of up in the air. My tentative was over next weekend. This was the calendar up to this point. I was hoping this weekend that this week we could, today we can just kind of knock out R6, R7, finish R8, and then probably have still some time on the 20th for that. But I'll share this once I see how in the world lecturing is going to go, because I'm interested myself. All right. So R6 is, and this is R6 and R7 are together here. R6 and R7, R6 is getting into complex numbers, and then R7 is applications. I just started the recording. Yes. So complex numbers. This is our introduction to them. And people always ask me, why do we have these? What's the point? Okay. The reason we have these is because they answer the question that we're asking. All right. What number, if you ask me to find the number that if I square it, I get 1. All right. Well, obviously 1 works. That's X, right? The negative 1 works as well, doesn't it? Yeah, that works too. So when I say, so if I switch that to ask you, when is this true? All right, when is x squared plus 1 equals 0? Well, you know that if you square a number, comes out positive, positive plus a positive can't be 0. And what I say to you is, nay, that is not true. Not every number multiplied by itself gives me a positive number. And that's what this is. Imaginary numbers are solutions to quadratics that we have. Something times itself plus 1 equals 0. Everything you run into up to this point, anything times itself ends up being a positive number. That's not what happens here. Now we have I. So I is the square root of -1, which means I squared is -1. And I like the notation from this book. You can see it both ways. If b is a positive real number, then the square root of -b is equal to I times the square root of b. What that means is if I give you the square root of -3, what's really going on there is I'm going to simplify this into -1 times 3 under the radical. And if I have the square root of products, I can rewrite that as the product of square roots. And I know that the square root of -1 is I. And the square root of 3 is the square root of 3. Can't do anything else with that. Okay, so that's just that's to make a long story unbearable. This is what's going on here. Whenever you see this, the negative pop out and become I, it's because what we're doing is technically we're factoring out a -1 and then saying the square root of -1 is I. Okay, so when do they come up? They come up in questions like this. I showed you an example of there on the top right, but if I get a quadratic such as x squared plus x is equal to negative 12, and I'm asked to solve it, what happens? Well, first, it's quadratic. And remember, solve a quadratic, I'm going to get everything on one side, see if I can factor it. Two numbers that multiply to 12 and add to 1. You already know we're out of luck there. So we have to use the quadratic formula. Quadratic formula says x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. And what am I going to run into? I'm going to get 1 minus 4 times 1 is 4. 4 times 12 is 48. And then at any other point, this is where we would all start to freak out and say, that's not real, it can't be. You know, ghosts aren't real, imaginaries aren't real. Because what happens? 1 minus 48 is under the root. And there's that pesky negative under the even root. Okay. So when that pops up, the way we handle it is we say that's square root of negative 1 is I, and then we continue the problem. But I'm going to ask this question on another page. So this is what we're after. What I want you to notice here is something under in the quadratic equation. What's under the radical there is called the discriminant. And the discriminant, if you are trying to remember your quadratic equation, what's under the root is b squared minus 4ac. Now think about this for a second. Everything you've done up to this point has come out, whatever's under here comes out positive, everything's fine, right? As long as that's positive, you end up with 2 real roots, and they are unique, they're not repeated. No. 6 and 7 are due, it'd be next Tuesday. Yeah, next Tuesday. Now, since I'm doing R.6 today, I'll push it too. But if you're done with it, excellent work. All right. So 2 real roots or 2 real solutions. Okay. If the discriminant is 0, that means you have a repeated root. So you have 1 real repeated root. And I'm just going to root and solution, same thing. And now what we're doing is introducing the situation where what's under the radical is negative. And in this case, you're going to get 2 complex solutions. All right, so the discriminant, just the discriminant itself, and when I say that, opposite of b plus or minus square root b squared minus 4ac, don't know why I'm saying it, over 2a. The discriminant, what's under that root, that's the controlling part, correct? Because in order to have a square root of negative 1, I need a square root. In order to have a negative, I need whatever's under the root to come out negative. So whenever this happens, you know you're looking at either 2 unique real solutions, 1 repeated root, or the other. So let's just get our beaks wet here. Simplify these complex numbers. Square root of negative 9. I'm not going to go into the detail I did above. The rule says if there's a negative out front, if I'm taking the square root of a negative real number, then I can just take that negative out, which is really, just like I said, it's you factor out a negative 1, the square root of negative 1 is I. Continue work though, because you're not done. The square root of 9 is 3. I don't have to consider positive and negative because I didn't take the square root of 2 sides of an equation, right? This is just one side. Whenever you write a complex number, unless you've got a root involved, the I typically goes at the end. Square root of 6, square root of negative 16. Now you're probably already ahead of me here. All right, square root of 16. Because again, what I love to do is try to do the problem in pieces, pay attention to the new part. The new part of this is the negatives under the root. Okay, well, if a negative is under the root, if this is a negative number, I'm taking the square root of it, I can just pop it out. Pop out that negative is the square root of negative 1, which is I, and now this is an old problem, right? Anytime we get a chance to do that, anytime we can make it look like something we used to do or we have done in the past, that's great. The last one here is not meant to be as tricky as it may seem. Again, you had the square root of a fraction. People start to freak out with fractions. Slow your roll. Hold on. I have a negative at the root of something negative. So the first step is going to be take that out. Okay. And now you can tackle this one two ways. Some of you may know what fraction itself gives me 1 over 16, or because of the rules of radicals, the square root of the quotient is the same thing as the quotient of the square roots, so I can actually split that. And the I will go over here to the right, not because it's wrong if it's on the left, it's just formatting. And square root of 1 is 1, square root of 4, I'm getting ahead of myself, square root of 16 is 4, and then there's the I. Okay, and I used to do I's like that. There we go. And people could read them. If you take an engineering class, or if you take an electronics class, physics, anything like that, you're going to find out that lowercase I stands for current. So when you get into those classes, if you need to deal with an imaginary, if you need to deal with I, the square root of negative 1, you'll see it represented as J. So don't be surprised if you see J instead of I in another situation. It does mean the same thing. All right? So, easy peasy, everybody's good. No questions, I'm assuming. I'm not trying to Jedi mind trick you into not asking questions. So let's tackle these last 3. I want you to do them. I'm not going to talk. I'm just going to do them along with you. I want to see what you come up with. And if you get into it and you just stop, right? The first thing, the new thing today, the thing I'm teaching you right now is there's a square root of a negative number. That means I can do this. If you can't go any farther than that, that's okay, because that's the new thing today. All right, so if we start with that concept. In the second one, my negative is on the outside, and then I have the square root of a negative 49. Well, the rule says that I can just take the square root of a negative. That's the same thing as I times the square root of whatever number was under there. So for the first few steps here, I'm not really doing anything except first thing I'm doing is the new step. Okay, let's deal with the 2 on the right and then come back to the one on the left, because the one on the left has some extra math involved. I have the square root of negative I times the square root of 49. That negative is not under the root, does not come out. It does not get replaced with a letter. It is there. It is along for the ride. Okay, it is the fly that got into your car when you left the house, and it's just going to buzz around until you get where you're going, or you finally get it out the window. Okay, it's in there. It's coming along with us for the ride. Square root of 49 is 7, and then formatting, the I goes to the end. The only time you'll see me not put I on the end on the right is if I have if I still have a radical, which is what you're going to see on that first one. Okay. Next, same game. I times square root of 9 is 3 times I times square root of 16 is 4. 4 times 3 is 12. I times I is I squared. Okay. Feels like we're done, but we're not quite done. X squared is fine. I squared is not, because remember, I is the square root of -1. Square root of -1 times the square root of -1 is -1, just like the square root of 2 times the square root of 2 is 2. So that means 12 times 1 leaves me -12. You'll never end up with a complex number that has I to any power. It won't have any power at all. It'll just either be there or it won't. It'll be power of 1 or nothing. Okay. So both of those, the one on the right, you'll notice you can multiply numbers, you can multiply complex numbers, and then end up with a real number as the solution or as the result of the product. On the left, let's come back over here. I times square root of 54. For me, is there a perfect square in here? It doesn't jump out at me, right? But I do know this is even. I know 54 is even. So half of 54 is 27. All right, 27 is 3 times 9. So all I'm doing is just writing 54 out in its factors, right? There we go. 9 is a perfect square. Okay, so the square root of 9 is 3. So that 3 comes out. Remember, the I came out at the very beginning. And then what's left under here is the 2 times the 3. I'd love to be able to do something else with that, but I can't, right? I don't have a mat, I don't have a pair, I don't have a perfect square. So the 2 times 3 just gets multiplied back together to 6. And there's nothing left to do. So this is that case that you'll see me put the I, it'll go after any constants, any real numbers, but it will not go here on the end. And the reason for that is simply if you put it here, it's really hard to tell if you mean for that I to be under the root or not. It's that one, it's more housekeeping for me than it is proper. But when you see me do that, that's why I'm doing it. All right. Yeah, everybody loves complex numbers. Everybody remembers this fun stuff. Questions? All right, so let's take all the things that we just did and answer the question that we started with. So if I want to deal with that original quadratic, x squared plus x plus 12 equals 0. Again, I added 12 to both sides so that I have a quadratic equal to 0, so that I can either use the quadratic equation or I can factor to get two things multiplied to give me 0. This doesn't work in terms of factoring. I can't multiply 12 and add to 1. So I have to use the quadratic equation. It says the opposite of b, which is -1 plus or minus. We've already done the work here. So I'm just going to go ahead and write it. Okay, and then we'll just make a little note here. Let's see, last page for work. What am I going to do now? Well, what I'm going to do is the same thing I've been doing as I've been dealing with the square roots of negatives. I'm going to square root of -47 is the same thing as I times the square root of 47 over 2. Okay, so what are my solutions? 47 is prime. It doesn't have any factors other than 1 in itself. So what I'm going to do, and you haven't seen me do this before, is I now have a complex number that has a real part and imaginary part. I have addition, subtraction over a single division. if that's the case, I can rewrite this as just 1/2 plus or minus I times the square root of 47 over 2. Okay. This is, again, a formatting thing. Whenever you have a complex number, you write the real part and then the imaginary part. And that's what I've got. And what's this going to do? This is going to split into 2 because I still have the plus minus going. So I've got -1 plus I times the square root of 47 over 2. And I have -1/2 minus I times the square root of 47 over 2. The only other way that you may see this, and the book I used to teach from was very particular about this, is since that root is in the numerator, it would put the I to the right of the fractional part of the complex number. But again, I'm more so telling you about the reasons I put things where I put them in the fridge, not because there's actually a reason, just because I have my own habits. So the solutions will be written as these pair of solutions. Anybody know what these are for each other? Take a look at the difference. What's the difference between the two solutions here? Everything's the same except for one piece. Right? The only thing that's different between -1/2 plus square root of 47 over 2 times I, -1/2 minus the square root of 47 over 2 times I, the only difference there is that sign in the middle. So these turn out to be complex conjugates. Remember that word? Right? Conjugates are just A plus B, A minus B. We multiplied them so that we could get radicals off the denominator. We're going to rerun into them again here. They're complex instead of rational because they have an I in them. That's the only reason. All right, so this is what solutions can look like. The book does a really good job of just trying to remind everybody -1/2 plus the square root of 47 over 2i is a complex number, not an imaginary number. Okay, imaginary I is the imaginary part. Complex numbers have a real part and an imaginary part. Sometimes the real part is 0 and they're just imaginary. But again, I've done a lot of work this semester on trying to make sure our vocabulary is correct. And the big thing in vocabulary here is imaginary is just referring to the I. Complex is referring to the number as a whole. All right. Now, what's changed here is up until this point, solutions to equations that required this taking the root of an even root of a negative number were not accepted or were not allowed. Now they are allowed. So what that means is when I go to solve things now, what I was doing before is I was solving over the real number system. Now I'm solving over the complex number system, okay? The complex number system contains the real system. You know, it's one of those squares. All squares are rectangles, not all rectangles are squares, right? So complex numbers have the form look like this, A plus BI, right? Where A and B are real numbers, okay? A is the real part, BI is the complex part. Well, if B is 0, if the imaginary part's gone, all I have is that real part. So all the real numbers are part of the complex system. Okay, they're just where the complex portion are 0. So when we say give me the complex numbers, just understand the reals can be contained in that. So when I'm solving over the complex, that just means I can end up with i's in the answer, and it is fine. So let's solve this quadratic. 48 plus m squared is equal to -1. Let's make sure we're still kicking. I know it's been a couple days. Typically, we get everything on one side, but what's missing here is the middle term. I see an m squared, but I don't see a term that just has m in it. And whenever that happens, that means I might get to use the square root principle. The square root principle says if I have some variable squared is equal to a number, and I want that variable to come out, or I want to solve for that variable, I'm going to take the square root of both sides. Before I wouldn't be allowed to do this, but now I am. Square root of m squared is m. And now be careful here. The square root of -49. We still have to pay attention to the positive and negative results of this. All right. Now finish the math. And we probably don't need to do this one in 2 steps. Square root of -49. The negative means an I is coming out. The square root of 49 is 7. So my answer here is 7i. But I've got the positive and the negative solution. So my solution set contains -7i and +7i. All right. Questions there? All right, in that case, let's go on and deal with our quadratic. This one looks like it would do nicely. Let's get everything on one side so that it equals to 0. Does everybody understand? Can everybody give me some hands up? Does everybody understand the difference in the attack on this, on the problem on the right? Why do I get everything on one side for this problem, but I don't do it on the other? Yeah? Yeah? Good. Excellent. It's a quadratic, right? And it has all 3 terms, right? A, B, let's say it another way. A, B, and C are all non-zero. Correct? All right. Okay, so get everything on one side. Set that equals 0 and solve. 2 things that multiply to 156 and adds -24. That feels like it should work, but it doesn't, right? So it's not always going to be something super multiply to 1 and add to 75. That's not going to always be the case. This one feels like it should work, but it doesn't. So it doesn't factor, so I need to use quadratic equation. Opposite of b means -24, which is 24, plus or minus the square root of 24 squared minus, that is, I was taught a long time ago that the sign of b does not matter at that step. So if you see me skip that part and just write it as positive, the reason is for some reason I'm still trying to save paper from 20 years ago. And I've done this already in my head. And -24 times -24 gives me positive. And then subtract the product here. And the result of this is -48. Okay. Now, that's the discriminant. The discriminant is negative, so that means the solutions to this quadratic are imaginary. Shoot, I just made like a huge long sermon about their complex, and then I say it wrong. All right, so let's deal with it. 24 plus or minus. I have a negative, so I'm going to bring out the I. And then, okay, as long as we remember to bring the I along with us, now this is an old problem. Square root of 48. 48 is 8 times 6. It's also 6 16 times 3, right? And which means that 16 times 3, 16 is a perfect square. Square root of 16 is 4. And can I do any more with that? Anybody need to see what in the world just happened there? Right? And now I can't simplify on the right anymore. I'm going to go ahead and split these up and write this as a complex number, a plus bi. So that's 24 over 2 plus or minus 4i times the square root of 3 over 2. Those simplify. 24 divided by 2 is 12 plus or minus 4i times the square root of 3 divided by 2. 4 divided by 2, the 2's divide away, leaving me at 2i times the square root of 3. And now I can write my two solutions because this is a plus and minus. Solutions here. The solutions here are 12 plus 2i times the square root of 3, 12 minus 2i times the square root of 3. All right. So here's that case I told you about before. You can see the I is not all the way on the right-hand side. It's not the last factor that I write for the imaginary part of the complex number. And again, it's specifically because if you put it on the end, it's easy to make it look like it's under the root. So, like I said, housekeeping, but it also helps you, prevents you from getting the wrong answer. And then when you go to type answers into ALEKS, if the I is on the end, if you type square root of 3, then you have to press the right arrow to get it out from under the root to then type the I. So I think it just helps altogether. All right. Last one is going to be done on video. Not here. Okay. But it looks like a big old fat mess, but it's not that bad. The key here is not to forget your roots. Don't forget the steps that you took to get here. And I have a quadratic. I have all three terms, A, B, and C are all non-zero. So we get everything to one side. And then I've got a fraction in the middle. I've got a fraction for B. I don't want that. So I have an equation. I have two sides. So I'm going to clear the fractions, and then I'm going to plug right into the quadratic equation. All right. Now, next part of this, U substitution. U substitution says what? Well, I've learned a whole lot, or we've learned a whole lot going through this process about solving quadratic equations. Take a look at the equations down here at the bottom, or down here below. I have x to the fourth minus x squared equals 42. If I get everything on one side, it's going to be minus 42 equals 0. That looks, if I squint my eyes a little bit, that if that were x squared minus x minus 42, we could factor this, right? Everybody would be able to factor that. 7 and 6, and negative 7 and a positive 6 to be specific. And there's my pen. I keep losing it. Minus 42 equals 0, right? If this were just x squared and x and minus 42, I'd have it. Well, I think I can make it look like that, because notice that the power of the leading, or the highest power, is double the next power, right? X to the fourth is x squared squared. something squared minus something, and I'm just putting it in parentheses to draw attention to it, minus 42 equals 0. So what I'm going to do is I'm going to let u equal x squared. When I do that, I now have u squared minus u minus 42 equals 0. And I just said that, man, I wish it looked like this, because if it did, this factors. Okay. Two things multiply to 0. One of them is 0. U minus 7 is equal to 0. U plus 6 is equal to 0. Solve for u. So u is equal to 7. U is equal to negative 6. And now we're going to resub. U is equal to x squared, which means I'm back in terms of x's. I have found that x squared is equal to 7, or x squared is equal to negative 6. For both of these, my next step is to take the square root of both sides. And as easy as it is to forget, you have to be super duper careful on the left-hand side, because, or excuse me, on the right-hand side of that second one, square root of x is square root of x squared is x, and the square root of 7 is the square root of 7, but I've taken the square root of a real number, so I gotta deal with the plus and the minus. On the right, I'm taking the square root of a complex number, or see, I'm taking the square root of a real number that happens to be negative. It's not complex until I take that root. So x is equal to the positive and negative square root of negative 6. Okay. Neither of these have any perfect square factors. Like negative 6 is 2 times 3. I can, of course, make this a complex number by bringing that I out. Okay. And so what do I have now? I have solutions. But instead of having my typical 2 solutions or 1 solution, I have 4. Right? The solutions for this problem include square root of 7, the negative square root of 7, I times the square root of 6, and negative I times the square root of 6. All 4 of those are solutions. Okay? If you're a pattern seeker, and if you're a human being, that's what your brain does, you may have picked up that this problem has 4 solutions. And if you look at the beginnings of the problem, the degree of the original polynomial is 4th degree. 4 degrees, 4 solutions. It's not always going to be the case. The degree of the polynomial and the maximum number of solutions available, they are the same. If I have a quadratic, if I have a square or degree 2 polynomial, it can only have 2 solutions. Can't have more than that. 3rd degree, 3. Think about a linear equation, just 1. Okay? So, questions. Okay, use substitution. On the right, I have another one. This one is more, in my opinion, this one screams use substitution a bit more than the other. The first, that one on the left, you really do have to, you almost have to know what you're doing before you do it. Over here on the right, I have this 2 plus 3 over t squared minus this 2 plus 3 over t, not squared, just to the first power, equals 12. Again, if I could make this look like a quadratic, I could factor it. Then let's let u equal 2 plus 3 over t. If I do that, now I have u squared minus u minus 12 equals 0. Right? Same thing as before. They're one apart. Multiply -12, add to -1, and -4 plus 3. Two things multiply to 0 by zero product principle. One of them 0. U is equal to 4. U is equal to -3. And then we have to do what we did before. This question was not originally asked about u's, it was asked about t's. So I need to resub the u is equal to 2 plus 3 over t. This one's going to be this is going to involve a little bit more work than the previous to get a final solution, but that's okay. So that means I have 2 plus 3 over t equals 4. 2 plus 3 over t equals -3. Everybody cool with how I went from there to there? Any questions on that? Okay. I've got t in the denominator. I'd really like to solve for it, so I need to get it out of the denominator. The easiest way to do that is clear fractions, but before I go clearing fractions, let's combine like terms. So on the 2 plus 3 over t is equal to 4, I'm going to subtract 2 from both sides. And what's that going to do? I should probably jot that down just because this is can be a bit of a mess if you're not careful. It doesn't affect the 3 over t. 4 minus 2 is 2. And now I'm going to clear the fractions by multiplying both sides by the LCD. Well, the LCD is what? Well, the denominator on the left is t. The denominator on the right is 1. I'm just going to multiply both sides by t. And what's that going to do for me? That's going to give me 3 is equal to 2t, which means t is equal to 3 over 2. On the right, I'm going to do the same as I did before. Get everything with a t on one side, everything without on the other. Subtract 2 from both sides. 3 over t is equal to -3 minus 2 more is -5. Multiply by LCD of t. And now I have 3 is equal to -5t. Finish it up. And t is equal to -3/5. I have checked both of these for solutions just to make sure. So my solutions, the solutions do check, are 3/2 and -3/5. All right. Questions? Okay. Silence terrifies me, but I'm going to live with it. I want to see you take a shot. So take a minute. Yeah, good, good. I'm glad. I am glad. So take a minute. We actually have a minute. And we're going to solve these equations. I've got 3 down below that I'm going to deal with on my own on video. But these top 2, I think we can tackle these without any trouble. So we'll do, I'm just going to I'm marking these as video for me. As you can see on the right, bottom right, that looks like a U substitution, but there's a bunch going on there. So we'll deal with that on its own. Okay. So like I said, I'm gonna be quiet for a minute. And I'm curious as to how you would want to tackle this. If someone wants to talk, you can. If you want to type, you can. If you just want to scribble furiously on paper and then see if it matches up with what we end up with at the end, that's fine too. All right. Ooh, you're right. Yes, I did. I just decided that magic was involved. Thank you. There's the I. There's the I. So there it sits. Good catch, all. Thank you. I knew the brain fog is real. All right. So on the left, end up with my two solutions. And again, you see my complex solutions are split up. I've written them as the real part plus the imaginary part. On the right, there's such a temptation there to say, I got two things that multiply to -34. This must be, this is my ticket out. This is an easy one. Remember though, that only works if I have two things multiply to give me 0. So I cannot do that. So in order to solve this, I'm going to distribute because that's the only math to be done. Plus 10m is equal to -34. It's a quadratic. It's got all three terms, so I'm going to put everything on one side. See if it'll factor. Multiply to 34, add to 10. Not going to happen, so quadratic equation gets called in. Opposite of b, plus or minus the square root of b squared minus 4 times a times c. Right off the bat, before we even finish writing it, you can see the discriminant. Because a is -1. Excuse me, a is 1. You can see the discriminant is going to cause exactly what we think should happen. 4 times 34 is bigger than 100. So I'm going to have 100 minus something larger than 100. Means the discriminant's negative, which means my solutions are complex. All right. So what exactly is that? 100 minus 4 times 34, negative 36. So that's negative 10 plus or minus the square root, negative 36 over 2. And that works out so beautifully because square root of the negative means I have an I need to bring out. And then the square root of 36 is 6. So that is plus or minus 6i over 2, which I can split up. And then there's actually division for both of these. A negative 10 divided by 2 is negative 5. 6 divided by 2 is 3. And my solutions are negative 5 plus 3i, negative 5 minus 3i. And there we go. So this one's just this is a heavy callback on old stuff. This is a heavy callback on dealing with factoring, dealing with being able to manipulate rational expressions, and then being able to write complex numbers. All right. So the last two I'll do for video later. Issues, questions, or problems there? No? Okay. I'm going to take your word for it. We're going to come over here to the word problems. So this is the R7 portion. So we'll tackle this and we'll call it a day because we're going to get through 2 sections today, which is great. So for this one, this is from the book. At the time of the printing, the highest special way of is there a special way of remembering the rule for the discriminant? The rule for the discriminant, as long as the discriminant is positive, it works like problems did before we got to this section. As long as it's positive or 0, it works just like before. There'd be 1 real solution or 2. It's when the discriminant is negative, which means, or when the discriminant is negative, that's when we use complex solutions for our quadratic. So yeah, no, the only way of special way to remember the discriminant is, in my mind, I just remember the quadratic equation and then I see what's under the root and remember that to be the discriminant. Okay. All right. So when this was printed, the highest vertical leap was 60 inches, held by Cador Zani. With a record-setting jump, Cador left the ground with an initial velocity of 8 times square root of 5 feet per second. How long after leaving the ground would it take Cador to reach his maximum height? Okay, so in this problem, or in this equation, we have S is equal to negative 16t squared plus 8 times the square root of 5t. Okay, so we're looking for a maximum height here. And what can I do with this? Okay. What do I want to know? What does this graph look like? Okay. Well, the equation or the function here is just telling me the height after t seconds. Let's take a look at the picture. I'm going to bring up a Desmo screen here. And let's just make sure this is even what we think it is, because I'm a little afraid. Yeah, because I thought I had done exactly what I said I was afraid of. And that T got stuck under the root. So let's make sure by looking at this picture. So ST is equal to negative 16. We'll find out if the answer makes any sense at all. 16t squared plus 8 times the square root of 5 t. And there we go. Okay. And what were we asked? We were asked, so what do I have? I have a parabola. It is facing down. So that's good. That looks good. That looks promising. Let me show you. I'm just curious at this point. If that T had stayed under, still a quadrat, it's still a parabola. It just ends abruptly right there. Okay. And the reason for that is because of real solution. Let's see here. T is time, S is height or position is what they would call it in the physics terms. So let me double check that. Let me make sure I've got the problem down right, because it may be that T may be under there. If it is, you know, that's great. Just deal with that later. So when I get highest leap is 60 inches, this is the initial velocity. How long would it take? Let's see what we can come up with. Any ideas? Let's stick with what I originally wrote. Let's just stick with what I originally wrote, and let's just see. Okay, so S is the height in inches, and T is the number of seconds after they've taken off, after he took off. And okay, so if I put that there, this is going to make more sense. So what do I know for my application here? Well, I want to know when, okay, and when is T. So I'm asking you to find T when S is equal to the maximum height. Well, they told us in the problem the maximum height is 60 inches. So when is S 60? Okay. So that means do what? That means plug in 60 for S and solve for T plus 8 times the root 5. And the parenthesis was there specifically to make sure that T came out. If that T were under the root, it would cause mayhem. But I'm not super confident this isn't going to be mayhem anyway. Let's see when it happens. What have we got? Okay, so it's a quadratic. It's not pretty. It's not pretty at all, but it is a quadratic. Everything to one side, plus 8 times root 5, T minus 60 is equal to 0. And then what? If I'm going to set this up, this looks like A is negative 16, B is 8 times the square root of 5, and C is -60. Okay? Now, my brain is not going to deal with that. Ooh, could we? Yes, we could. Ooh, that's an excellent point. Ooh, wait a second. 8 times 5 is 40. No, because that 60 is frustratingly not divisible by 8. But I could get a 4 out of there. I'm going to leave this one. Let's go down and tackle the one below it, because I don't like how if I've set the problem up wrong at the beginning, I'm just inviting a whole bunch of error to pop into this problem without the necessity for it. So I'm gonna, again, tackle this one on the video and post it. My bad. This is COVID brain. I get to have an excuse. And let's just deal with this problem instead, because it's deer walking in the road. That's way more exciting or terrifying or sad. The distance required to stop a car that was traveling at speed V in miles per hour before the brakes were applied depends on the amount of friction between the tires and the road and the driver's reaction time. So you got a couple things going on. You got to have good tires and you got to have good reaction time, and a decent road. After an accident, a legal team hired an engineering firm to collect data for the stretch of road where an accident occurred. Based on the data, the stopping distances given by this equation determine the distance required to stop a car going 50 miles an hour, and up to what speed to the nearest mile per hour could the motorist be traveling and still have adequate stopping distance to avoid hitting the deer. Okay, so let's tackle part A. Part A says, my equation says that the distance to stop is equal to the square of the velocity of the speed the car is traveling times 0.05 plus 2.2 times the velocity of the car. Okay. One of these is the brakes, the friction between the brakes and the road, or the tires of the road, and one of these is reaction time. Okay. So this is the equation. I want to know how far, what's D if the speed I'm going is 50 miles an hour. Well, that just means if V equals 50, find D, right? We haven't seen a problem like this before where I just give you a quadratic, but instead of saying solve the quadratic, I'm just saying here's the value for the variable that's in there. Solve it. Okay. Calculator comes to the rescue. 0.05 times 50 squared plus 2.2 times 50. I get 235. And these are feet. Anybody disagree? Okay. You all are old enough to drive now. You know why speed limits at night are. If you've driven in Florida, if you ever been down there, you may have seen signs where there are different speed limits depending on day or night. And at night, the max speed is 55. During the day, 65. And the reason is we don't realize how far the car will travel between our ability to stop the car, what we see and stop. And if you're driving faster than 60 miles an hour with bright lights on, you can't see far enough ahead of you to know you need to stop. So that's what this is. It's going to take 235 feet to stop the car given that equation. Part B was up to what speed could a motorist be traveling and still have adequate stopping distance to avoid hitting a deer 330 feet away. Okay, so in this one, we have the same equation, d is equal to 0.05 v squared plus 2.2 v. And now if d is equal to 330, find v, right? So it's same equation, but they flipped it on us, right? They flipped it on us, and now they gave us d. They asked us to find v. This looks more like a problem that everybody's aware of, or we have just been dealing with. D is 330. And solve. That's a quadratic. All three terms are there. So I'm gonna get everything on one side. I'm gonna do that by subtracting this 330. And I'm gonna find out that 0 is equal to 0.05 v squared plus 2.2 v minus 330. Looking at this one, I don't really gain anything. The fractions are fine. Quadratic says that the solution is the opposite of b, 2.2 plus or minus the square root. Does anybody think, do you think the discriminant is going to come out positive or negative here? I know we've been dealing with complex numbers. Do you think the discriminant is going to be positive or negative? Think about the type of problem we're doing. All right. So not only do we not have to worry about the discriminant, not only is it work, but take a look. Yeah, we're going to have to be positive. Take a look at the discriminant. I got 2.2 squared minus, well, the product of 4 times a times c is going to give me a negative number. So I've got something minus negative something. That's going to come out positive. That means I'm going to get 2 real solutions. All right, so 2.2 plus all of that. 2.2 squared minus 4 times 0.05 times negative 330. Under there gives me negative 2.2 plus or minus, I've got 70.84 over 1/10. All right, that's going to split to 2 answers. Right, I got a plus and a minus. So one of these is negative 2.2 minus 70.84 divided by 1/10. Gives me negative 730.4. And then the other one is negative 2.2 plus 70.84 divide by 1/10. I did it in the calculator, but I didn't take the square root. Man. Thank you. I did all that math and then didn't take this the square root. You guys are on it today. I like it. Square root 70.84. There. That's why this is off. I tried to be clever, but then didn't show my work, and it cost me. Sorry, that's 70.84, and then you take the square root is 842. Okay, so good call. Yes, I got you. So Finish it up. One of these is going to be negative, one of these is going to be positive, right? This is a real world problem. So that means the negative one doesn't do anything for me. 106.2, but the positive one might, or the positive one does. Negative 2.2 plus 8.42 divided by 1/10, 62.2. This makes no sense, and this one does. This is miles per hour. It fits the story because remember the last one? The last problem above at 55 miles an hour or 50 miles an hour is 235 feet to stop. And now I'm saying if you need 330 feet to stop, you can be going all the way up to 62.2. All right? Okay, so we got the video done. If you got questions, send them. Other than that, have a great rest of the day. And look out for videos. All right. That's all right.